Good afternoon, everyone. Just as a quick reminder, remember that the homeworks are going to be due today at the end of the day, so make sure to get those in. And then in terms of other deadlines, I hope everyone has maybe at least started to think about projects, and it'll, like I was saying before, it's a good idea to meet with me or email about project ideas so that I can give some feedback before the proposals will ultimately be due in a couple of weeks, I believe. Hang on, let me pull up the date so I can just confirm. Yeah, so the projects proposals are going to be due on May 5th. So definitely coming up. So make sure to start thinking about that, looking at data sets and that sort of thing. And definitely reach out to me if you have any questions or concerns about the project. Okay. So today we will be finally sort of departing from the linear models that we've been sort of building on throughout the course. And we will be talking about logistic regression, which is going to be essentially a natural extension of the modeling that we've been doing so far, but applied to a specific type of question, namely having to do with what happens when your response variable, your y, is not a continuous variable. So we've talked about how we deal with that with discrete variables for your x's, right? When you have dummy variables and categorical variables. But the sort of meaning that takes on for once we extend that to the response variable is slightly different. So let's talk about logistic regression. So this is a regression model where the response / dependent variable is categorical. And we're going to start with simple examples. So simple examples for binary outcomes. But this will extend to multiple outcomes. And that type of model is known as a multinomial logistic regression. As a form of sort of nomenclature, in machine learning, they refer to this as something different. So whenever you guess a binary / categorical outcome, this is known as classification, which makes sense. You are essentially attempting to classify something, your output, into these discrete outcomes. In other words, we have some, for our simple binary choice, we have our input, the model, which is what we're going to be, sort of talking about, and then kind of a yes or no, or a 1 or 0 type of outcome, or true or false. So this type of model, you can imagine is actually fairly common and sort of prominent in data analytics, particularly when you're dealing with certain types of data. For example, in transportation, if I'm talking about like vehicle adoption, it could be something like, are you going to buy a car? Yes or no. And then the things that might influence this, our X's, could be income, education, race, so on and so forth. And so similar to the linear model, the input X's can be both continuous or discrete. And we will see in a little bit how the interpretation of these X's on Y, or the influence of the effect, right, can be interpreted in this particular type of model. And it's going to be a little bit more complicated, and I will try and show you guys in sort of my opinion, better ways of doing interpretation for logistic type models, which oftentimes suffer from being much more difficult to interpret. Okay. So let's back up for a second and talk a little bit more fundamentally about this. So how do we model this? I think that when a lot of classes kind of introduce this concept, they really jump into the theory and sort of the derivation of like a logit function, and then thinking about the error distributions in it, how it gets applied, and then how you run the model and that type of thing. But I think it's important to take a step back and think about why it is that we do a logistic regression instead of a linear regression, because that'll help, I think, guide our understanding of why this is done in the way that it's done. So how do we model this? So one, linear to represents probability between 0 and 1, but not bounded. So this is like the first kind of basic step of how you could do a model like this. So we think about our traditional model of X and Y, where you have points that look something like this, and then we just run a line through it. Okay, but now it's a little bit less straightforward. We have our X's and we have our Y's. So you may have a lot of variation along your X, but in your Y's, oops, you can only have a binary outcome. So your x's, oops, sorry. So your x's might look something like this. And your y's might look something like this. And if you were to run a linear regression, you may end up with a line that kind of looks like this. And so what does this even mean? Like, oh, the interpretation of this line is kind of obviously different from, you know, the figure on the right, right? And so oftentimes, you know, in the cases where this is done, and I will say, you know, people still do run kind of your regular old linear regression on these types of outcomes. Oftentimes, you know, it's like a probabilistic thing between 0 and 1. They take the slope as a way of translating the probability of a y outcome happening. Which is sometimes reasonable, especially if you're really only concerned with like average effects of your x. But you can imagine that this type of model is probably not well suited to do anything in great detail. Additionally, there's from a more sort of like mathematical viewpoint, you've got something a little bit more fundamentally weird happening, which is that, okay, if you accept this, like if you accept the explanation about the probability when it's between 0 and 1, well, the line, you'll notice, extends below 0, and it also extends above 1. And so therefore, the interpretation of, you know, what y is when you're in that territory is kind of like nonsensical, right? You can't have lower than a 0% probability. You can't have greater than a 100% probability. And so that line, if it's something that you are actually doing, is only really valid in this sort of narrow range window. And for that reason, you could do something, you could do a type of transformation on the data. And so we've actually talked about this before. You could log the probability of x. So this is multiply inputs together, but unbounded in one direction. Okay, and so if you do that, this will solve the problem of falling below 0, right? Because you can't have a log of x being a negative number. And so that is why essentially you've done this is to prevent, you know, going below that threshold. And then you could actually figure out a way, if you were to log p of x over 1 minus p of x, if you do a further transformation of the data here, this will allow you to bound on both ends. And so this is where the logit function comes from. So this is the logit transformation. And generally, this P over 1 minus P is known as the odds. So this is success, and this is failure for any particular outcome, right? And so the odds are the chances that you win versus the chances that you lose. And to show a graph of this, so when we do this log transformation, let me actually, oh, okay, I need some more room here. So this, this is essentially going to be our new y, right? So that's what I was saying before. When we do the 0 and 1, sort of treating as a probability, p of x is the y. So in step 2, you're just logging it. In step 3, you are transforming into this logit, and then the rest of it is still kind of like a linear functions. So y log odds, or the log of odds. We can draw a graph to show why this is. So if this is our probability, if I map this from 0 to 1, we can now see that the odds will be bounded in 0 and upwards to infinity here. So we go 0 to infinity. And if I do the log odds, I can go from 0. So hang on. So this is the odds versus the log odds. The graph will look something like this. And so your log odds go from negative infinity to positive infinity. Okay. And again, thinking back to this original justification from going from step 1 to 2 to 3, the whole point is that we want this line that we draw to extend across the full range of possible values of x going to infinity to negative infinity. So by doing all of these transformations, we then allow for our regression to not be sort of artificially bounded by the sort of range in the data and having these sort of discrete values. Now we can go back to being able to say to extend the explanation of the fit across your sort of full negative infinity to infinity values. Okay. Any questions? All right, one moment. Let's show an application of this in R. Okay, so this time I did put the data on Canvas ahead of time, so hopefully everyone has access to that if they want to follow along. We are going to show an example of running a logistic regression in R. Okay, so we've got some election data. Let's go ahead and take a look at it. It's a pretty simple data set. This is some old election data about different districts in the United States, and there are only two variables here. We have our outcome variable, which is whether or not a Democrat wins a particular election, versus this other column, which is the percent of registered Democrats within that district. And so, you know, this isn't actually like percentage of votes or anything, right? Because just because you have fewer percentage of registered Democrats doesn't always mean that the Democrat will lose the election. And I think you can actually see that here. Like here, for example, this is less than 50% Democrats, but they still win. So here is an example where we have a set of binary outcomes against a continuous variable of percent registered Democratic voters. So now we're going to use a function called GLM, which is a generalized linear model. And we're going to look at the Democrat winning as our response variable, right? And there are two outcomes, 0, 1. So it looks like this, except that we also have this extra thing that you have to put, which is your link function that I talked about before. And this is basically specifying the type of distribution and error term in this type of model, we're looking at a binomial distribution, right, where you have two outcomes. So I will sort of go ahead and run this. And let's then take a look at the results, which are going to be, I think, somewhat different here. Okay, so we'll notice that a lot of the diagnostics are going to be a little bit different. And then we'll look at these estimates, negative 23.8798, and this estimate 48.2926. Okay, and so let's take a second and think about the interpretation here. If this were like the old linear models that we've looked at, then it would be, I guess the interpretation would be something like for every 100% increase in number of registered Democrats, then the outcome would increase by 48, right? So that is not how you interpret this, right? And so this sometimes I'll see people making this mistake where they'll look at sort of logistic regression outcomes and think about it in the same way as the linear models that we've been talking about. That interpretation just doesn't really make sense, right? Remember, our ultimate outcome of the Democrat winning is just a 0 or 1 thing. So what the heck does this mean? And so let's jump back into the notes to see how I would actually go about interpreting this and why it's not the same as a linear model. And the very first thing to remember is that we are not doing y equals beta 0 plus beta 1x. Okay, we are looking at a logit transformation where you have log okay. We have log p of x over 1 minus p of x. So these values here are meant to reflect the response in the log odds ratio. And you could actually you could actually go about and interpret those numbers in a particular way, but it's a lot less straightforward, and it also depends on sort of the level, right? So just to give a sense of what that would mean, so let's say at 50% registered Democrats, you have this 48.2926 value. This is for beta 1. You could actually go and calculate how your log odds ratio changes by increasing, this value by if x increases by 0.01, right, which represent a 1% increase in number of registered Democrats. That would then affect your log odds ratio in a certain way, right? So it would be, so I should also write down our so this would be negative 23.8798 plus 0.482926 is equal to the log of your probability here. And you could go about sort of calculating this to sort of backtrack to your ultimate outcome of figuring out how it affects how likely it is that the Democrat will win. But it's also nonlinear, right? Remember that chart about how it relates to the log, that the probability relates to the log odds. And so the actual effect of the coefficient will change at different levels of x. Okay, so the interpretation gets really, I think, complex and less straightforward when you are thinking about it in terms of the odds ratio. And for that reason, I typically encourage folks to think about it more in the probability space. And so the way that we would go about doing that is kind of as follows. So we want to solve for P of X, the probability of your Y outcome happening. So P of X is equal to, so if I simply simplify the math, you end up with something that looks like this: exp of beta 0 plus beta 1x divided by 1 plus exp beta 0 plus beta 1x. And this is known as the inverse logit. So I could actually go about and calculate this. So the probability when x equals 0.1, it would be, right, exp of negative 23.8798 plus 48.2926 times 0.1 divided by 1 plus exp of the same thing. Okay, and this is about 0.010325. So this gives us a better, sort of more direct relationship with the probabilistic outcomes, as opposed to if I were to just interpret this version, which would be a unit change in the log odds, which is really kind of difficult to interpret. And so I definitely kind of encourage interpretation of this rather than of this.
I have a quick question.
Yep.
So since our x is itself bounded by 0 and 1, is it a 0.1? Is the coefficient refer to a 0.1 increase, or is it like a 1 increase?
No, it refers to a 1 increase. That you could so.
Oh, never mind. Since we're plugging it in, we just plugged in 0.1.
Yeah, exactly. It's I think, yeah. So the difference is like in the linear one, we used to say this, right? Beta 1, x1. So as x1 goes up by 1, then y goes up by beta 1, right? But in this case, it's if you have it as this, then the interpretation is as x1 goes up by 1, then the log odds increases by beta 1. And yeah, okay, and maybe this is a more clear sort of way of putting it, which is if you have it as this way, you're saying as my x changes, then the ratio of the odds or the log odds ratio will increase by beta 1, which to me is like, I don't really know what that means. It's really kind of hard to interpret. Not only, I mean, interpreting the odds kind of makes sense. It's a little bit trickier to think about, but then interpreting the log odds is just kind of, to me, it's kind of like nonsense. But if you do it like this, where I have P of x equals you can say, you can now say something about how as x goes up by some quantity by 1, then the probability of y will increase by some quantity. Okay, and so that quantity depends on everything that's going on here. but at least you'd be able to have some way of kind of discerning a real outcome.
Is the quantity the exponential term, like all of it?
Yeah, 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 that's right. And so basically, well, it's actually more straightforward just to kind of plug in an x and figure out what the probability is. So let me jump back into the R example to give a sort of practical comparison of these two interpretations, and then I'll sort of let you guys kind of decide which one will be easier to interpret. Okay, so one moment. All right. So like I was saying, the way that a lot of the interpretation happens for the inverse logit is you just plug in x's and then you figure out the probability of the outcome. So it's a little bit different. So in this case, what I'm going to do to help myself interpret this model is I'm going to set it up so I'm going to basically pass in a bunch of values into the model to predict the probability of the outcome. So I'm creating a new data frame where it's going to say that the percent of registered Democrats is between 0 and 1 in increments of 0.01. And then I'm just going to pass that on as a prediction. So similar to the linear model, we can predict certain outcomes. And the new data that I'm plugging in is that new vector that I just made. And we can actually make type equals response. So in here, there are actually a couple different types of predictions that you can now generate. So I'll show this one first. Let me make sure this is all.
I think it's just a typo. You have response instead of response.
Oh, right. Yes. Yeah, there we go. So let's take a look at this. So this now gives the probability outcome. You could have a different type of predict outcome. As you can see here, if I want to do like the link, it will be, this is the actual odds ratio at different levels of registered Democrats. So if you did want the log p of x over 1 minus p of x term as the outcome instead of the probability, you could see that here. But we're going to be looking at the probability curve. So I'm just going to graph this very quickly so that you guys can see what this looks like. So on the x-axis, we have the proportion of registered Democrats. And then on the y, we have probability that the Democrat candidate wins. Okay, so let's take a look at this. Oop, I need ggplots. Okay. So here we can see the probability corresponding to any sort of particular outcome. Remember that it's usually instead of a 0 or 1, we are now, for any value of x, giving a probability that you see the one outcome actually occurring. You could actually have a predictive response based on your actual outcome. And usually the way that people do that cutoff for these binary ones is they just say, if the probability is above 0.5, you give it a 1 value. If it's below 0.5, you give it a 0 value. So you could actually do the prediction of yes or no, the Democrat will win. And so the real sort of punchline of what I'm doing here, right, which is really quite different from what we've done in the linear models, is that, you know, my kind of display of the results is that I'm showing you this probability curve, so that I can look at a particular x and tell you the probability that the outcome occurs, as an alternative to looking at trying to interpret our direct coefficients from the model, right? And so when we think about the way people interpret logistic regressions, in reality, when they generate these tables, they don't actually try and make any deductions about the changes in the log odds ratio or anything. They kind of just say, okay, well, it's statistically significant. We know that the effect is real and that it's positive, which means the more registered Democrats you have, the more likely it is that the Democrat will win the election. Okay, that's basically the type of interpretation that you commonly see in presentations or in papers when they interpret this. But if we think about it in the probability space, you know, I am of the opinion that this graph is kind of a lot more informative about what happens to the outcome as a result of changing your X, in this case, changing the proportion of registered Democrats. Okay, any questions about that?
Could you explain again what the response does, what link does when you have the type?
Yeah, sure. So remember that in the linear model, when we do predict, it just predicts the Y. And in this case, we're asking, when you do the predict, you can predict the, need to turn on the pen. So you can predict P of X. You could predict log of P of X over 1 minus P of X. And then you could actually also just predict your Y. So if you predict this gives probability of outcome. This gives the log odds ratio. And then hopefully you can see that. Sorry if this is a little less clear. Actually, I'll use a different color. So this is probability of outcome. This is the log odds ratio, and then this is the outcome. And then when you use the type of response, it is, I believe it should be giving you each of these three possibilities. So when you do type equals response, that'll give you the P of X, the probability of any outcome. If you do link, it'll just give you the log odds. Oh, wait, this is not the log odds. This is the what is the link? Actually, okay. I don't want to say anything wrong. I think I know what it is, but let me double check it and I'll get back to you. I don't want to report the wrong information. And then the last one that you can get, look at it. So I believe this one. Oh yeah, go ahead. I hear someone.
Yeah, this is the log of the probability, I think.
The log of the probability?
Yep. If you do the log of 4.25, it will give you minus 23.87. Let me send you in the box.
Yeah. They're logging the probability without dividing. Okay. That's not what I thought it was. Actually, this is not what I want either. I think if you do it like this. 1 second. No, that's the default is the log of the probability. Okay. Yeah, I thought that they had one that gives the actual outcome when the probability is greater than 0.5 or your break even, but I guess not. Okay, so let me get back to you about why that is. I need to double check on something, but okay. So the link is going to be the log of the probability outcome. Okay.
I think I found the page that describes it. But they, under arguments, they have type and they describe what each type response means in terms of a binomial model.
Yeah, okay. So the terms option returns a matrix giving the fitted values of each term in the model formula on the linear predictor scale. Yeah, so that should be, yeah, so terms should, oh, okay. No. Yeah. So I was describing wrong. So if you do, let's just do this again. Okay. Democrat, so this is the probability, just to be extra clear. Okay, so in the predict function, so the two types that you should be familiar with that on what they do are type equals response and type equals terms. Response gives you the probability outcome associated with a particular X. And then the term outcome gives the fitted value, which is the log odds ratio at a given value of X. Yeah, and so this term here is going to be is going to be that log odds ratio for your linear term. Hopefully that is clear for everyone. And you can actually see yeah, if you do like the calculation for 0 in your X, you can see how that relates to the coefficients directly. All right, so let's take a quick break. Right now, let's do a 5-minute break until 3:13, and then we'll continue on. And in the meantime, if anyone has questions about this, we can chat more.
Just to clarify, so response gives you px, and terms gives you like the log odds ratio, right?
Response gives you p of x.
Right.
Yeah, it gives you the probability of an outcome given an x. Yeah.
And terms gives you the log odds ratio, right?
Yeah, exactly.
Yeah, I had a quick question about the homework. I just want to make sure there isn't a typo on problem number 2, the credit card limit section.
Yes, go ahead.
So is level 5 and level 6 for education, are they both supposed to be unknown?
Yeah, so the data set as it came had 2 classifications for unknown for some reason. Yeah, it was kind of just built that way. I don't know why.
And level 0 for marriage is also unknown then?
Yes, that's correct.
Okay. Thank you.
Yep.
Hi.
Hey,
Alan, I think that the link it it works with the log odds too. I think that I use another sample. I will send you now, and it gets the result of the log odds. Sorry. Yes, I send you in the chat. It's for.
I see. But this is your.
This is the 0.14, I think. 0.14. Let me see. 14. No. 3. Yeah. Okay. Let me see. No. Okay. This is not 2, 3, 4. Is 0.47. It gets the log odds. Yes, because I used in the first message, I used the first one. So at the end is the same because the denominator is 1, so it won't change. But with the value in the middle of the table, it gives the log odds.
So you're saying it's like the link is the one. Yeah.
Yeah.
Okay. That was my initial impression.
Yeah. I will try with other value.
Yeah. So, okay. I guess the reason why I don't know this part so well is because no one really operates looking at the predictions of the log odds. It's always about, if you're doing log odds, you don't really go beyond looking at the summary results table. Really, the transformation to the probability is something that people understand a lot better. And so, that this one is the one, this line 9 is the one that you should arguably always do. I kind of wanted as a reference to provide to you, information on what the other types of predictions you could get out of the model, such as the log odds. It's possible to do that rather than calculating it manually, and so you could in theory do that, but in practice it's very rare to do that.
All right.
Yeah.
Well, so it's just to clarify this, the link is also for the log odds. I try with other observation and it works.
Yeah, good. Okay, one moment. So let's continue onwards. Oops. So the next thing that we'll talk about is the next step in generalizing a logistic regression, particularly in response to the dependent variable, the response variable y, and thinking about how a binary set of discrete outcomes can be extended to, you know, multiple categorical outcomes. When we drew the probability chart, so this is percent registered Democrats, and then probability of outcome, which in this particular case is Democrats winning. There was this sort of line here for my P of X that says Democrats win. But in reality, there's one other line. You actually have something like this, which is 1 minus P of X. In other words, this is Democrats losing. These are your two possible outcomes. And we're working in probability land, right? So anywhere I draw a line, the line probabilities must sum to 1. So if I add this point and this point, or this point and this point, or this point and this point, and so on, that's the world of our possible outcomes. And it's always going to add to 1. So we're going to kind of retain this information as we move forward into multinomial logistic regression. So this is a generalization of logistic regression to multi-class problems. So let's talk about this. So we have a binary. So originally we had a binary outcome. So I'm going to write it in a slightly different way. It's okay. This is outcome, comma I. This is our observations. Equals beta 0 for k plus beta 1 k x 1 I. And hopefully this kind of makes sense to you guys. We in the binary example, we actually omit one of the set of betas, and that's because of this whole thing where you can get at the value of the probability for the other outcome simply by doing 1 minus. So usually you don't show betas for all of the outcomes. It's all -1, which is going to be how we think about the multinomial as well. So again, just to be sort of extra rigorous about this, right? If this is the original betas in that example, if I run back here, that is the betas for this blue line here. And then you've got a different set of betas for the red line here. But we don't show the other set of betas. And if you remember the table, you've got percent Democrats here, and then Democrats winning. So you have 1, 0, 1, 0. So in this case, K has only 2 outcomes. So in a multinomial logit, also known as M and L, you have multiple outcomes instead of 2 outcomes. So this F of Ki is equal to, some vector of betas for each outcome corresponding to your x's. The only difference is that now K can be greater than 2 with a different set of betas for each outcome. And in this case, if we think about our probability space, so X, so if this is X, and this is P of X, then, or let me do it like this. Probability, then you could have now multiple lines, maybe like that. Okay, my drawing's probably really bad, but P of X, P of Y, P of Z, all lines must add up to 1. Okay. So let's take a look. Add an example in R. I'm going to bring in a couple other libraries, ISLR, here's some data set, nets. So we're going to look at a data set called car seats. Okay, let me. So here's an example. It's got sales, price, income, advertising, population. So comp price and price, shelf location, age, education, So this is about, this is looking at the sales data of baby car seats and individual purchases with attributes about the consumer. And so it's kind of a contrived example, but we're going to look at how whether or not there is a sort of relation between the shelf location on price and sales. It'll usually be kind of the other way around, but let's just take a look at what this relationship kind of looks like. So can we say anything about the shelf location based on the price of the car seat and how well it sells? So our Y variable, the shelf location of the car seat, is classified into 3 groups. So instead of having a binary outcome, we have 3 different discrete values: bad, good, and medium. And we can see how those relate to the sales and the price. So I'm using a slightly different function here than I was doing before, because it gives certain types of outputs that are a little bit nicer for sort of doing transformations into the probability space. So this is a package from NNet called Multinom, which is specialized for running multinomial logistic regressions, which is exactly what we're doing right now. And so if I run this, you'll see this kind of message happening. And that is actually having to do with solving for the betas. So this is like detail that we don't really get into in this class. But when we think about a linear regression, you know, I've talked about how there's this closed form solution that you can do, you know, the X. So it's your beta is equal to xtx minus 1 of xty. So you may have seen this equation before. And so that is a closed form solution for obtaining your betas. When you do a logistic regression, you actually have to go through a numerical method, a maximum likelihood estimator, to calculate the betas. And so that is kind of what's happening here. Is it's showing you some diagnostics of the of running the algorithm that finds the numerical solution. Okay, so when I do the summary of the model, we can see a set of coefficients here, which is a little bit different, right? We have the intercept, the price, and sales. These are our betas. But like I was saying, you now have a set of betas for every outcome of Y, because it's telling you something about the log odds ratio, of one particular outcome relative to the other ones, which you can also use to calculate the probabilities. And because they're interrelated, right, because the probabilities always add up to 1, they will always only provide they'll always provide n minus 1 sets of coefficients, because the last set can always be calculated from these coefficients. Okay. So I have a little bit of built-in code here, so that I can look at the probabilities really quickly. If you look at if you use the effect function, I can show you what this does. It will tell you the probability associated with one particular set of outcomes. So the way this works is I now have to guess at the probability across, because I have 2 variables, both the price and the sales. And so you actually have like instead of a 2D distribution, it's kind of 3-dimensional. So what you could do is you can hold either your price or your sales fixed, and then look at the probability outcome changed here. So that's what the MNL effect does. It is looking at a particular variable. In this case, we're looking at price, and it's going to hold the sales fixed to the average value of the sales. And so I'll just run this code so that you guys can see what's happening here. So at the average level of sales, we can see how the probability that the car seat is located on a good shelf, a bad shelf, or a medium shelf changes over a range of price, over different ranges of prices. And so at the sort of lowest prices up to the highest prices, you can see that the bad locations decrease with higher prices, and then the good ones increase. And so this is basically saying your probability of improving the location of the shelf, right, going from bad to medium to good, sort of continuously goes up as the price increases. Okay, hopefully that makes sense for everyone. Any questions about this? So this is, again, the kind of analogous chart to that Democrats probability one, where you go from less registered Democrats to more registered Democrats, and then your probability of any outcome increases. This is the same thing, but where we have multiple outcomes. Instead of just 1 or 0, you now have bad, good, medium.
So in this graph, for the probability, it also has like a confidence interval or like a range. Is that also included in the results?
Yeah. So there is oops, in here, there's standard errors associated with each coefficient. So actually in our original plot, let me go up here. Oop. What's going on? Oh, oops, here we go. Yeah, so in the default one, so there is some uncertainty in the beta, right? And so any particular outcome has some uncertainty associated with it. So if I were to pick x equals 0.5, like right here, you can actually have a little bit of uncertainty. And so that creates this like, well, I'm sorry, this is a really terrible line. It usually will look something like this, as like a lower bound and upper bound type of thing. And that's not actually in this one. And that's part of also why I like the effects package, is that it can explicitly draw in those bounds. And so when I look at this plot, this includes the 95th confidence intervals about our estimate of the probability based off of uncertainty and the standard errors for each of the coefficients.
Okay, got it. Thank you.
Yep.
And I have another question. Sorry. For the frequency, I'm a bit confused. Is it the x that you picked that is like the other x that is variable, or is it something else?
Yeah. So this, yeah, I didn't change the label, but it's sales are fixed, and then this is price, and it's just that, like in the original one, you know, we did this predict over this wide range. Here it's just doing a predict over 5 values of price. That's all.
Yeah, okay, thanks.
Yeah, you can make, if I did a prediction, I think the effects package will, unless you specify what you want to predict on, it chooses 5 values. But you can make these lines look a lot smoother, you know, if you predict over a larger number of price values.
Yeah, I see. Thanks.
Mm-hmm.
Is this output saying that if the price increases, the probability of buying a good quality car seat goes up?
No, sorry, yeah, no. So the variables that we're actually looking at in the data set in car seats, so there are these 3 variables. So this is our y, this is x1, this is x2. It's not the greatest model, but it's one where I have this available data set on hand to show this. But it's basically saying, if you change the price and the sales, how does that affect the shelf location of the car seat, of the baby car seat? So they put them on shelves in the stores, and we classify them as the shelf location as like good, bad, and medium. And it's probably like bad is like if it's really high, it's too high for you to reach or something. And medium might be like you have to stoop down to reach it. And then good might be like really present and visible and easy to reach, that sort of thing. It's kind of a silly example, because they're probably probably the shelf location actually influences the sales, right? But I need a categorical variable in the y to show as the example. Okay. Any other questions? Okay, so I want to show one more thing in relation to this multinomial logit model, which will kind of help us kick into next class about topics looking at classification. And also this actually touches on what I was saying earlier about classification as well. So classification is a term for looking at these outcomes, looking at categorical outcome variables. And so the sort of disciplines that work with logistic regressions, vary from economics, statistics, machine learning, and so on and so forth. And what I've shown you so far has a lot more to do with interpreting effects of X on Y, right? So thinking about what the coefficients mean, and then thinking about sort of, in my view, better ways to interpret some of the influences of your X on your Y. But like I said before, a lot of a lot of this modeling, we're oftentimes more concerned with prediction of outcomes rather than understanding relationships between variables, between your explanatory variables and your Ys. And so let's kind of adapt this model that we've created to focus more on those predictive aspects rather than these X relationship to Ys. And the way that we can do that is to essentially use that predict function to look over a range of all of our X's and figure out what the Y's will look like. And we can sort of map that out. And as I would almost argue, a different way of employing our model to look at essentially a different sort of outcome than sort of the regression table and these probability plots. So I'm going to look at sequences of my prices based on the lowest to highest, and I'm also going to look at the corresponding for the sales, so from lowest to around the highest. Seats.new. So this is the new data set that we'll be inputting. Seats.new. Okay, and let's go ahead and plot this. Okay, so let's look at what our predictions look like. Nope. I have some error somewhere. Sequence from 24 to 199 by 1. Oh, actually, sorry, the function was wrong. It should be expand grid, not expand. Okay, let's try that again. Yeah, great. So this is an example that you would see much more often in really what we're talking about as classification, right? In like a machine learning application where I can look at a new set of inputs to do predictions. And in this case, I can even kind of compare directly against the original data to kind of see what this looks like. And so you can see how the logistic model creates these linear boundaries about each of our dimensions of our input parameters to classify the outcomes. So you can see at certain combinations of sales and price, you have these linear boundaries, which is an artifact of the fact that we are still kind of working in linear space here, right, with our betas and their relationship with the x's. And you can see, again, at certain combinations, which ones it predicts are going to be bad, which ones it predicts are going to be medium, and which ones it predicts are going to be good. And we can look at this and see how that compares against the actual sort of data points here. We are going to look at a couple other examples of classification methods. Now, when we think back to the linear models and we think about which types of models are the best, right? We were thinking about all the stuff about criteria. So like looking at R squared, AIC, BIC, looking at the mean squared error. These are all ways in which we can compare different types of models. And so we're gonna be doing kind of the same type of thing for classification, but our metrics are gonna be really different, right? Because, you know, there isn't really the types of classification models that we're going to be looking at are actually going to be pretty different from what we think of as like traditional regression-based approaches. And so, you know, what does it mean to have like a mean squared error for a type of regression problem where you're doing this like logistic transformation. So you might think intuitively, you know, there are other types of metrics that we'll be looking at. And so I think one obvious one that kind of jumps out in this type of figure is the error rate, right? I could actually go in here and I could say, I could just count how many times my prediction is getting it is getting the classification correctly, right? So green in the green background, correct, correct, correct. But then I can jump over here and I can say, oh, there's a blue dot here when my model is predicting that it should be green. Okay, so incorrect, right? So you can look at, for example, the total number of incorrect counts for your outcomes. You know, anytime I get the color wrong, and then I can add all of that up and say, okay, for this type of model, my error rate is I got like 30% of them wrong out of the total, compared to a different type of model where I get like 25% wrong, and therefore I would favor that. And one other thing that to keep in mind, it's not as kind of intuitive or obvious in this particular example, but you may care a lot more about specific types of outcomes. So if you've ever heard of like type 1 error or type 2 error, it's related to this concept. So let's say that you are doing some kind of you're devising a kind of model that tells you whether or not you are going to test positive for like coronavirus. You can imagine that I care a lot more about your false negatives than your false positives, right? Because if I tell someone that you have coronavirus and you don't actually have coronavirus, okay, that's kind of bad, but the person quarantines for 2 weeks and it's kind of like this, your outcome is this person loses, 2 weeks of their life. Whereas if you have a false negative, then you could be like essentially infecting a whole bunch of people because that person thinks he doesn't have coronavirus. So the analogy here is like, I care more about blue dots in the red area than red dots in the blue area. That's kind of the analogy here. And by using different error metrics, by caring more about type 1 error versus type 2 error, or type 2 error more than type 1 error, you can actually you can use that as a different type of metric. And when we do model comparison or variable selection, you may find that you can boost your total error, right? Your total error rate will go up, but your type 1 or type 2 error will go down because you've tuned the model that way. So we're going to explore this concept a little bit more as we delve into more sort of classifications, but that's kind of just to give you guys a taste about how the classification metrics for what we consider as good quality models is going to be pretty different from the metrics that we think about when we try to get the sort of quote unquote best models for linear models. Okay, so that's where we're going to end today. I will go ahead and stick around for any questions. Otherwise, I'll see you guys all on Monday, and don't forget to submit your homeworks by the end of the day today.